presentation level, so but one day you will be. So my name is Diogo Lança. I'm from the FabLab Luxembourg. I'm the FabLab technician, and today I'm going to present a project that we did of a 3D printer, designing from scratch, but looking at it not as a commercial thing to sell, but more as how we can use this machine to in our FabLab, and how can we integrate and bring people around this technology to promote the FabLab activities and also educate at the same time. So a little bit of background, I'm from the University of Luxembourg. I did my master's there in mechanical engineering, and then after that I joined the FabLab Luxembourg. I've been there since July, and during my work there, or any FabLab, you see a lot of people, and you go to events with the machines, and you see how people react to all the tools, but the 3D printers. And here you can also see that there's a fascination around this technology, something that we can take advantage to educate and to educate. So it's always like the first question in any show is, can I touch it? It's like people are like scared and they think that this is like some sort of magic. So they are interested, but they are kind of scared to get into this. And then they start asking more interesting questions, like how does it work? How can this print? How is this like science fiction? But I'm seeing right now. And then how is the object created? So they are interested in modeling, 3D modeling. So how can we reach to the point where we can print something? And then more interesting questions like how much it costs. Everyone knows here that it's been going down the cost, so you can buy a 3D printer for 200 euros. It's no problem. And then is it difficult to operate? So is it difficult to maintain? Do I have to invest a lot of time to get into this? And all of these questions show the interest. And there's a very good opportunity for us to educate and to involve. Educate meaning to teach people that a 3D printer can be designed and is designed for a specific purpose. So we can show CAD, so Inventor, Google SketchUp, so how to design something, not just a 3D printer, but it's already a very nice case study. And also involve in the community, because if you are working in the FabLab, one of the big challenges is to build community. It's to involve people and make sure that they come back so that we can work with them and they can learn. So we thought about this 3D printer as a way to bring people together to learn and to involve and make sure people come back. So a lot of this surrounding the 3D printer, so it's an open source community, and also it's the guidelines of this project, so everything will be open source, and there's demand and curiosity that opens up people to learn better and faster. And also the technology is very wide, so in terms of getting tools and getting, even for the FabLabs to buy the components to build this machine is already very accessible, because there's a big community of makers that are doing 3D printers. So if you go to Amazon, you can find everything. That's how we started with the first prototype. And then it's a technology that is simple, but yet challenging, that we can cover from beginner to advanced. So all of this is very nice to start designing a printer for the lab. But then you may ask, why design a printer from scratch? There's already tons of it, like probably one comes every day, new design, and you can go around this event and see a lot of different machines. So why? So the first main point is flexibility. You are designing something that you have an experience because you are working with a lot of different printers, so you can kind of already know what's working and what's not. So you can pick and choose the components for this printer that works for your FabLab. Some FabLabs have more specialty, so for example, in our FabLab, I'm engineer and the FabLab manager is an architect, but there's other people that have different backgrounds. So adjusting and making it flexible so that the machine can be adapted, so you can change everything. So it showcases, of course, the techniques and the capabilities of the FabLab. All the structure is made by tools in the FabLab, so you can even, we're going to talk about the workshops that can be potentially used for this machine, but all the structure is made in the lab, so you can fabricate everything in the lab. Of course, components like motors and smooth rods you have to buy, but that's very specific. And then it starts the educational program around this tool, and we're going to talk a little bit more about that. And goes in line with the objective of the FabLab network of the FabLab 2.0, which is the FabLab building tools and make a FabLab. So first the manager buys all the tools and then installs a FabLab, but then it's kind of expected that the FabLab starts building their own tools. So the requirements for this machine, any design starts with requirements. So first is only tools available in the lab that you have to use laser cutters, 3D printers to make the machine. So everyone has that except in their FabLabs. It's easy to find components. Everyone should be able to go to their local stores or Amazon and should be able to relatively with ease find these components. It's not special, special nuts, special bolts. And it's a compromise between precise and local. So we want to find that balance. Where can we build a printer that doesn't cost a lot of money, but it's still precise enough to be a 3D printer, because that's the point, to be precise. And easy to assemble, so everyone should be able to assemble, should be an easy to assemble machine that FabLab people can assemble, but also kids. So, and it's open source, so and upgradable, and this goes in line with the Creative Commons we want to attach to the machine. This basically means that attribution, you have to reference who made it, and you have to share alike, meaning that you have to share with the same type of Creative Commons, so you cannot change it to your liking. This is to protect everyone. So there's a lot of printers that move differently. So kinematics means just how they move. So if you know a Prusa moves differently than a Ultimaker, and then we have to decide which one can we use, going into a line with these requirements I just talked about. So there's a lot of things that I don't during the design process I wanted to avoid. So a lot of printers, they move motors when they are moving in the axis, so we don't want that. We want to make it light as possible so that we can go faster printing speeds, and also no closing belts, so no closed belts. So also this goes in line with easy to find and cheap components. So it's much easier to just buy a big belt like 5 meters and just cut it off and for your specific needs. And this is so this type of special components that I was talking about. So the printer is designed around the core XY kinematic system. This is so with a printer, if you want to go X, you move a motor, or go X, and you go Y, you also have a motor. And this doesn't work like that. So if every motor turns in the same position, so the same side, it moves to an axis. If they move different sides, they move another axis. And this is used exactly because all the motors are stationary. So this is the plate that we attach everything, so everything doesn't move in terms of the motors. And then in red and blue you see the open belts, so the systems that make all these connections between the motor, and this should be the hot hands where you actually print. And also this allows us to go faster in terms of 3D printing speeds. And then there's no special components because it's open belts. So we are moving in that direction of the requirements we established. So easy to find components, there's nothing special here. Smooth rods with linear bearings, open belt pulley, bearings from like skateboards, so there's nothing fancy here. And this is the X and Y, like the core XY plate. So all these plates is milled or is laser cut. We use plexi, 10 millimeter plexi, to do this. So everything is made using digital fabrication in the lab. So we know that everything is precise and it's easy to assemble. Everything is assembled to this one component. So we are using open source electronics, also nothing fancy. M8 lead screw for the Z, and all metal hot hands because we think that it's the most reliable at the moment. So we are trying to make it so that you have to, it's easy to operate. This is the first prototype. I don't know if you can see properly. So this is some characteristics. So core XY has a heated bed, of course, all metal hot end, the Bowden system. This means that the motor to extrude is attached to the structure and not in the carriage, like a Ultimaker. And an SD card, so all the minimum requirements, let's say, for a machine to start being upgraded. So on the left you see the 3D model, then in Autodesk Inventor, and this is the first prototype. So again, open source. These are the nested parts for the laser cutter or for the CNC milling machine. So this depends on what the lab wants to use. Also 3D printed parts. Maybe I go back. So all the connections between the plexi and the more complex structure are made using 3D printed parts. So we want to take advantage of this technology to make all these weirds and connections, to make it easy also to assemble, because they want to be easy to do that. So some features. So the machine, in terms of building volume, is 20 centimeters by 20 centimeters by 20. So I would say it's like the bare minimum to be able to do something nice. I did the ratio, so it's just a division between the dimensions of the machine and the respective axis. So this is done just to be comparable to other machines in terms of size. So as you can see, there's still some room for improvement, that's the point, but it's still not very far away from the dimension of a normal printer that we can find. Costs, so 400 euros just for materials. So this was done again by ordering from Amazon, and sometimes you have to pay a little bit more, like in weight for shipping, all of that. So not much was done to, well, we try to make it as cheap as possible, but sometimes you have to order and you want to make it faster. So there's a lot of ground to be covered there. Also, this includes all the plexi parts for the structure, but it can be used something else. We use that because it's a solid material, but you can use any type other that you can cut with a laser cutter or a milling machine. So that will go up or down in costs. So this printing resolution, I don't know if you can see properly, but just for a small test, from 0.3 will be like the lowest quality that you would print, to, I would say, one of the more fine quality, 0.05. So the machine still has some vibrational problems that need to be addressed. Printing speeds, I was able to print at 150 millimeters per second. I didn't push it too far, but this is already a good printing speed. Again, a lot of ground to be covered, but we can already see the potential of the machine. It's very precise for the type of construction that it has. So how would we use this machine to use it in our day-to-day lives in FabLab with the community? So first can be used as a case study for how to design a printer in this case, but can be also done, and the principles can be extracted how we can design anything. So starting by the requirements, conceptual design, and looking at what really is necessary to be to the final stage, and then making a product that fits those requirements. And then after that you can actually make the machine. So using tools available in any FabLab, you can design, you can make what you designed. So it's already a nice transition there. Can be two separate things or just one continuous. Then you can go to assemble in electronics, and you can talk about. So you're using here the Marlin software to use to program. So Arduino programming can be introduced. Also assemble techniques and how to make the printer. At the end, of course, comes actually printing and calibration. That can be a very long process. And if the user went through all these steps, they can then ask to go back to design. So having into account all of this, how can we make this better? How can we make the printer better? What is working here? What is not working? And here the community comes together, and it can be a nice platform. So all of this can be different workshops, or it can be a big one, where you start with the machine design and talking about CAD modeling, and then you make it, you assemble it, you actually test it, and you go back to the drawing board and keep going and make it a better machine. So closing remarks, I don't know how long I have, yeah, perfect. So it's flexible, so that we can adapt it to the day-to-day life in the FabLab, and it can be improved without not much effort, because it can be, all the printed parts are 3D printed, so you can improve that. You can design better attachments using the community as a melting pot of ideas. It's in-lab assemble and productions, so you can ask the users to make the structure. At the end, they can make it like a package that they learn all of these things, and at the end they receive the printer, and this will attract a lot of people because they already know the whole stage, and if they know how to maintain it, and if they are confident that can they take the machine and fix it, or because they have a whole overview, they can much easily get into this technology. And I think it's a little bit of the objective of FabLab to educate. So this removes a little bit of the fear and the can I touch it questions. Workshops and community building, of course, everyone will be around the FabLab to do this kind of project, and it will bring people together. They have ideas, they come, they can improve. One improvement can affect all the users in that community, because if we have one big idea and good idea, everyone will benefit. So it's taking advantage of design by everyone, but locally made. And it will be nice to start spreading this idea to other FabLabs, and then because it's open source and it will be available for everyone to download, they can start benefiting the users, because they will have something that was designed for the FabLab environment. And also one big issue is that everyone has a different printer and everyone has different problems. Even not just FabLabs, but users. Sometimes people come with a machine that we never saw, and we really cannot help them that much, or we have to spend a lot of time to get into that machine and then help them. If you can provide a printer that they feel confident using and everyone can help each other, that would be great. And also continuous improvements of the machine itself, but also the people that are working with it. So users and also the people that work in the FabLab. So that will be the end. I will make like if you have some questions. This is the QR code. You can scan it, or you can go to that link where you can see more pictures of the machine and also a video of the machine actually working, because it's working. I don't have it here, but I want to show that it's actually working. It's not some fantasy. If you have some more follow-ups, you have our email. You can follow us on social media, and if you have any questions, feel free to ask me. I'm sure you have a lot. Yeah, so the question was if we want to make something bigger, if it's scalable. Yes, we're actually working on that, of in the design make it parametric, so that you want to define the limitations of it, so the build size, and then the structure adapts automatically. I would say so of course we are limited by the type of heated beds that you can find, and also the smooth rods, but if that's an issue, we can jump to another type of kinematic, not using smooth rods, but using aluminium beams. So it will be nice, so that's also adaptive. So if you want to use something else, but we're working on that, of making it so that you just type whatever, I don't know, probably not 1 meter by 1 meter, but I mean, make it so that it's easier for people to choose, because probably they don't want a bigger printer, but they want a smaller one that fits that corner, and if 10 by 10 is enough, why not provide it? And it's not very difficult to do if you can make a parametric model, and everything is digital fabricated, so everything should be adaptable, so there's no problem there. Thank you. So this machine is just for plastic, so FDM printing, so filament deposition modeling. It's just using the filament, but we are working on like a small adaptation, just changing the extruder so that we can do paste extrusion. So using clay, food, and that's also the point. Metal, that's a different technology. That's way advanced. But plastic and paste extrusion should be feasible with this machine. Yeah. Okay. Thank you.